Okay, so we have tangent vectors on R2 considered as a real vector space, right? They have the set of tangent vectors, the vector space of tangent vectors has dimension 2. These are the basis elements. And if you consider the dual space, we define these gadgets as the dual vectors of or covectors of these two basis elements. So they satisfy these relations. And for the complex variable z written like this, we may just let dzp as this gadget, and then z bar is this, of course, and it will be like this. Now we wonder, what about this directional derivatives? Okay, directional derivative along z and along z bar. Okay, now let's see. Well, whatever that gadget is, so let me see. Let's say del z p is just some a times del xp and b times del yp. Then I know what? I know that dz evaluated on this should be 1, and dzp z uh, bar p evaluated on this should be 0, because these two again will be the dual elements for these covectors. If you open this up, so dz is just 1 over 2 times dx plus, let me just skip the p from the notation, okay? And then this is just a times del x plus b times del y. And I want this to be 1, and we want this gadget 1 over 2i dx minus I dy. Here I forgot there is this I here. And yes, a plus. So we want this to be 0. No, this is plus again. I'm sorry. So let's see what we get. Well, dx is 1, dx dy is 0, dy dx is 0, and dy del y is just 1. So I have 1 over 2 times. From this I will get a. From this I will get 0. And then from this again I will get 0. dy on this gadget is 0. And then we have this b times I times dy del y is equal to 1. And what about this gadget? 1 over 2i times dx del x, it gives me a. This will give me 0. This will give me 0. And then here I have minus I times b times 1. So we get this. And this is 0. So what we see, then a plus bi is equal to 2, and a minus bi is equal to 0. So from this, if you add this up, you get 2a is equal to 2. So a is 1. And if a is 1, then b is just b times I is just 2 minus a, but a is 1, so this is just 2 minus 1, which is 1. Therefore, b is just 1 over I. So what we see is then, hence, del del z t is just a times, right, a times del del x. So it is just del del x at p plus b times this gadget. B is equal to this gadget, or if you multiply both sides by I, you get minus I, right? Minus I squared is just 1. So I have just b times, so minus I times del del yp. Okay, so there is a surprise here. So this time this is not plus, it is minus. And similarly, what is del del what's z? If you just repeat, the same thing, take this thing and write C here, D here, and repeat all these, you will see that this is just del del x at P. This time it will be plus del del y at P. Bir bölü 2 olması gerekmiyor muydu? Ha yok, orada şey var. Tamam yok. Bir dakika. Şurada şeyi unuttum. E, burada burada 1 bölü 2 yok. Evet. Şurada 1 bölü 2 yok. Dolayısıyla burada da yok. Sorry. Burada da dz bar buydu. I don't have this. Burada bir şey değişmiyor da. I have this. So this is 1. I'm sorry. This is 1. Şeyi yanlış yazdım. Dz p'yi 1 over 2 yazdım. Dzp is just this. Dx plus I dy. So I have this. Therefore, this is just 1. And this is 1 over 2. And this will be just what? Bi is just 1 minus I. So 1 minus 1 over 2 is just 1 over 2. So this is just I over 2. So I have to be careful. I'm sorry. Neyse, böyle hata yapınca şeyi de görüyorsunuz. Çok kolay hata yapabilirsiniz. Del del x p minus I times del del y p. And this time here, this will be similarly 1 over 2 times del del x p plus I times del del y p. Şurada şeye dikkat edin. Bir remark. Remark şu. A function f from C to C given by, f z or f x plus iy as uxy plus ivxy is holomorphic at a point, or analytic at a point P, if and only if and only if del zp of f is zero. Neden? Bakalım. Well, del zp bar f equals zero is if and only if. What is this gadget? This is just 1/2 times this gadget. So 1/2 times del x at p plus I times del y. Şunu düzgün yazayım. At p evaluated at the function p. So u plus I times v equals zero. Well, this is if and only if. What? If and only if. You just open this up. 1/2 times x derivative of this, right? I am taking directional derivative. So this is a function of two variables, x and y, and you are taking derivative with respect to x. So this is just u sub x at the point P. Ya da onu en sonda yazayım. And then I times v sub x at the point P plus I times, again, u sub y. This time I am taking derivative with respect to y. And then I times I, which is minus 1 times v sub y. Evaluated at p equals 0. But here you see I have real gadgets and imaginary parts. Let me just separate them, and let's get rid of this 1/2 because I have 0 here. So what we see is then the real part u sub x minus v sub y plus I times u sub y plus v sub x equals 0. Well, I have I have a complex number, it is equal to 0. That is equal to 0 if and only if both real and imaginary parts are 0. So this should be 0. U sub x minus v sub y should be 0, and u sub y plus v sub x should be 0. And that's just the Cauchy-Riemann equations, right? So this is if and only if u sub x equals v sub y and u sub y is equal to minus v sub x. So a function is analytic if and only if its del bar derivative is 0. Okay? This is something we will use over and over. Okay? Anlaştık mı? Peki. Şey sorabilirsiniz. İntegralde hani fx dx'in integralini alıyoruz, değil mi? Oradaki dx ile buradaki dx aynı mı? Evet, aynı. Yani o notasyonun şeyi bu. İntegrali öyle tanımlayabilirsiniz. Yani bir differential integrali öyle tanımlayabilirsiniz. Peki, bir de şöyle bir şey var. Onu da yapayım. Also, note that dz Wedge dz bar. Tabii wedge'in de ne olduğunu geçen sene lineeri benden alanlar var mı? Tamam. Onlar biliyorlar. Geri kalanı da videoları izlesin o zaman. Wedge product değil mi? Tensörün bir şeyi. So I have so dx wedge dx plus dx times this. So minus I times dx wedge dy plus I times dy wedge dx minus I times minus I times minus I is just minus I squared, which is plus 1. Oh, so this is 0. Ha, o da evet. Bu da dx wedge dx. Tamam. Şimdi oldu. Bu da I squared dy dy. Well, we know that this is 0. This is 0. So what we see is then and we know that dx dy and dy dx are inverse of each other, additive inverses. So if you interchange two terms, you get a minus sign. So this is just minus 2 times dx dy, or equivalently dx dy is just 1 over minus 2I times dz bar. Bunu da isterseniz şöyle yazabilirsiniz. 1 bölü eksi i demek zaten, değil mi? Çünkü i ile çarpın her iki tarafı. I minus i squared is just. Why this is important? Because, this is the area form, okay? When you integrate over a region in R2, this is the area form, right? This is something you integrate over regions. So that area form can be written like this in complex coordinates. Okay. Let C be a Riemann surface. Not necessarily compact, I guess, with holomorphic coordinate covering. UI zi, a differential one form, lambda on C is given by a family of local expressions lambda I which is defined on this u sub I in this coordinate, and it is like this: fi zi bar. I will explain this notation: zi dzi plus gi zi bar dzi bar. Here, where fi and gi are smooth functions, not necessarily complex, analytic, or anything. Smooth functions which obey the transformation laws. Nedir o transformation law'ları? Yani eğer bir koordinat değişimi yaparsak, suppose I have a coordinate system here, zi, and here I have zj, and we have ya da ters şöyle olsun, okay, zj, zi, and suppose zi is just phi ij zj, okay. All right. Now, here I have this expression written with zi, and here I have the same thing, but this time I have lambda j, fj, and so on. And I have to tell you how the expressions on this coordinate system and on this coordinate system looks like. And here, how it looks like, or how it is transformed. Bu tabii aslında yani birinci sınıftan beri bildiğiniz şey, koordinat değişimi. Başka bir şey değil. Okay. So f I phi ij zj, and then so this is my zi, okay, zi, and ij zj bar. So this is zi bar, and then this thing will be just multiplied with the derivative of this function f sub j zj bar, and the same thing for this gadget ij zj zj bar d phi ij zj bar dzj equals zj bar. Let me explain, why we have to define it this way. Kim tanım bittiyse yapayım da. Tamam, tanım Burada bitmiş mi? Şimdi on an open set, okay, in R2, let's say, if I have a one form, any one form can be written like this. So, what's the one form? Tabii onu da söylemek lazım. Well, at each point, I have this dxp and dyp, right? This covectors. You just pick a covector at any point, okay? Therefore, a one form is something like this. A function, let's say, f xy at the point, and then times dx. I should write p. So whenever, you know, so let's say p is just xy. So plus some other function, and then the other one form, right? At any point, I have a basis of one forms, dxp and dyp, and at each point, I just pick one. And we ask these functions to be smooth. So we ask them to be smooth functions. Smooth functions of R2. So they are infinitely many times differentiable, okay? In this case, we will call this a one form. You are actually familiar with this gadget from differential equations and so on, right? You have such expressions. You ask whether it is integrable or not and so on, right? But here, you know, instead of writing everything in x and y coordinates, I could just do the following. Z is just, x is just, you know, z plus z bar over 2. Y is just z minus z bar over 2i. So if you just replace all these things becomes function of z and z bar, and this will be dz and dz bar, dz and dz bar. You can rearrange them and write them just in this form, right? So every one form can be written like this also. Or you may go backwards, you know, right here x plus iy, x minus iy, and so on. You can write everything in x and y. So these are just you know, two different coordinate systems, nothing else. And here we ask, of course, you know, now on a Riemann surface like this, suppose I have two coordinate systems like this. I have here ui and uj, and here I have the function here zi, zj, okay? And here we have zi'yi şey cinsinden yazdık değil mi? Zi, evet. So it's going actually this way, phi ij. So zi is just phi zj, okay? Hmm. Evet. Şöyle Tamam. Şimdi mutlusun. Tamam. Okay, so here we have, of course, something like this, right? So we are actually choosing a point here that will correspond to, this opposite will correspond to something like this and something like this here. And this function is defined on this piece. Okay, now what is differential of this dzi? Dzi, okay. Onu da söylemedik. Şöyle yapmak lazım. If you have a function, let's say u x y, what is the differential of this? Du is just this. You take derivative with respect to x, dx, plus derivative of y, derivative of u with respect to y, dy. So this is the differential of a function. Okay? Bunu tarif ettik mi daha önce? If you do it in this coordinate, again, you can just do it this way. So if you consider this as a function of z and z bar, then this can be also written as u sub z dz plus u sub z bar dz bar. Okay? So if I change my coordinates x and y to z and z bar, then this is what I get. So this thing is just what? This is just derivative of this gadget with respect to z and well, dzj, of course, this gadget, and plus derivative of this gadget with respect to zj bar dzj bar. But the thing is that, you know, this function is holomorphic. So this thing is holomorphic. Okay, it is not just a smooth function, but it's holomorphic. Therefore, this derivative is 0. So this, coordinate change affects the differential form like this. Okay, so this implies dzi is just this gadget. Okay, that's why here in the Jacobian only has this gadgets. Okay, there is no derivative with respect to z bar. Okay, our differential form here we have the z I, and here we have dzj, and here we have the zi bar, the zj bar. Şurada bunun zj bar'a göre türevini almamız lazım herhalde. Mi? Çünkü bunun konjugesini alırsak bu şey değil. holomorfik değil. O yüzden şurada z bar olacak sanırım. Yani o ilk zaten burada yazdım onları. Kitaptan bir kontrol edin bunu da. So here I should have z bar I guess because I have bar here. Mesela bu identity olsaydı, so if this function were identity, ij identity, so z equals z, then the bar of this would be this. So I have dz okay, so derivative of this, so derivative of this gadget with respect to dz would be 0, but if I have this gadget, then I have double bar here. So derivative of bar of z bar, but this thing is just z with respect to yok. Yanlış yapıyorum. I'm sorry. This is not what I would say. I was okay. So if this function is identity, then this is just dz bar, and derivative of this with respect to z is just 0. That's why I should have bar here so that this is 1. And identity transformation, of course, shouldn't change anything. So I should get 1. Therefore, I should have bar here. Otherwise, I would get just 0. So this is a typo. Tamam, ben yanlış yazmışım. Tamam. Okay. Bu kadar yapmaya gerek yok ama hani nedeni de o. Tamam mı? Öbür türlü anlamsız zaten. Peki. Onu da yaptım. Şuraya geçeceğiz. Bir tanım daha var. Onu da vereyim. Hatta 2 tane daha tanım var. Ondan sonra teorem gelecek. Tanımları vereyim, bitsin. Okay, so next definition is this. Ondan geliyor. Neyse. The exterior derivative of a differential one form lambda, suppose it is given in local coordinates like this, gi dzi bar, değil mi? A one form has this expression, is defined as so this is definition. Şöyle yapacaksınız. Del gi del zi minus del fi del di bar times dzi which dzi bar. Şimdi bunun için de isterseniz bir açıklamayı yapayım kısaca. So we have zero forms. Zero forms are just functions, okay? So these are just functions. So fxy, okay? F from, let's say, an open set u into r or c, whatever. Okay? For a zero form, its exterior derivative is just df. So df, which is just f, so what's that? F sub x dx plus f sub y dy. So this is a one form, and this is the exterior derivative of the zero form f. Yani functions are zero forms, their exterior derivatives are defined like this. This is definition, okay? It's definition. df is a one form and it is defined by this expression. We were calling this differential of f, but differential of f is indeed actually the exterior derivative of the zero form. Now for a one form, for a one form, I have, so one forms. What's a one form? One form is something like this. Let's say fxy dx plus gxy dy. You have seen this stuff in advanced calculus, right? What's the exterior derivative? Its exterior derivative is defined as, bu da tanım, as the two form, bu two form, nedir o? dw, it is just, you just take the exterior derivative of the zero form, so df, and then you write dx here, plus dg dy. Now what is df? df is just f sub x dx plus f sub y dy. You wedge this with dx plus what is dg? dg is just g sub x dx plus g sub y dy, and you wedge this with dy, and then you have what? You take wedge product. I have dx. Okay, let me write f sub x dx, f sub y dy dx plus g sub x dx dy plus g sub y dy. And we know from linear algebra that this is dx. dx is 0. So this thing is 0. Again, this thing is just 0. And dy dx is just minus dx dy. Therefore, we see that our differential is just g sub y minus bir dakika, şurası g sub, pardon, g sub x dx dy g sub x dx dy minus f sub y dx dy. Okay. And what are two forms? Two forms are objects like this. Two forms. Since we are always locally in R2 or C, R2, we have only one two form basically. So any two form is something like this. Some function h xy dx dy. Or if you write in coordinates here, so here I have z x and y, and here I have z and z bar, or we get z bar d z dz bar. Okay. And so a one form has this expression. Here again, you know, if you write dx and dy in z and z bar, you will get an expression like this. And its differential is given via this formula using this definition here. You know, I am using this definition. Differential of a one form is this gadget, which is just this. If you just write everything in z and z bar, you will just get this gadget. So let me just leave it to you as an exercise. You know, derive this formula from the real formula. Yani x, y'li, you may take this as the definition of the exterior derivative of a one form, and then change the coordinates z and z bar, write this thing in z and z bar, and see that this gadget in z and z bar is just this. Okay? Diyebilirsiniz ki yani differential niye böyle tarif ediliyor? O sorunun cevabını bilmiyorum ama bu right definition. Neden? Çünkü işte hesaplarla uyumlu. İntegrali tarif edeceğiz. İntegralde işte Stokes teoremi vesaire var. Onların çalışması için bunun böyle tarif edilmesi lazım. Tamam mı? Bu exterior derivatif geometrik bir anlamı da var. This exterior derivative via Stokes theorem becomes something very geometric. How? Now, suppose you have some region, okay, omega, and we have its boundary. And suppose we have a differential form here defined on the boundary. Suppose this is n-dimensional, boundary is n-1 dimensional, and suppose that this is an n-1 form. N-1 form. Its exterior derivative d omega will be an n form. And Stokes theorem tells us the following. Integral of omega over the boundary of this gadget is just integral over omega of the exterior derivative. So taking exterior derivative of a differential form is basically the same thing as taking the boundary of a region. So this is something very, geometric, topological, and this is something analytic. You take derivatives and so on. But they are the same thing. Okay. That's why, this thing is, although it looks like, something artificial, it is not. Okay. It's something actually very fundamental. And it corresponds basically taking the boundary of a region. Yani Stokes teorem bunları birleştiriyor. Okay, let's stop here.